Okay, so we'll start then. Yeah, I was just checking if my stylus is working. Okay, so we'll start now. These are already know. We covered things from Cheng, the Smith chart part. So we did Smith chart and everything from Cheng. We are again back to Mozart doing resonators, and we are here. So we're starting module 8 today, and two classes, and then we'll move to microwave filters. So today and next class we'll try to finish power. So today we'll finish power dividers, and the next class we'll do direction couplers. I hope I'm still audible. Can you confirm once again if the voice is fine? Again, using my tablet actually.
Yes, sir, it's fine.
It's fine, right? Okay. So in the last class we finished microwave resonators, parallel resonant circuits, loaded and unloaded queue, and transmission line resonators. So we'll just quickly uh, do a revision. Uh, yeah, just give me a second. Yeah, sorry about that. I'm actually visiting my home and it's a little crowded here. Yeah, sorry. So we'll resume. So the last class we were doing microwave resonators, and we'll do a quick revision now. So, so we looked at the parallel resonant circuits. The the previous class. So the class before the previous class, we looked at the series RLC circuit, and the last class we looked at the parallel RLC circuit. So we have the RLC in parallel over here, and the Z input is calculated by using this expression over here. And then similar to the what we did for the parallel resonant circuits, we did it for the CD. For the what we did for the series, we also did for the parallel. So we calculate the input power, and then we calculated the power lost across the resistance, the energy stored in the electric field in the capacitor, the magnetic energy stored in the inductor as Wm, and then this expression was given by the Poynting theorem. Now, then we expressed again the input impedance in terms of power and the current, and we had this expression over here. And for resonance, what we the criteria is to make this term equal to 0, and so we equated these two terms, and upon doing that, we got the resonance frequency given over here. And when this particular part becomes 0, which is this part, so our input impedance was equal to power lost by I square, which is equal to the resistance. So this happened for the parallel resonant circuit. And then we had this expression over here, and we used the binomial terms to simplify this. So this is all maths, and then we ended up with something which looked like this. So this form is important. We'll use this later. And then we also had defined this term, the quality factor over here, which is given by these expressions. So you can remember all of them. They're pretty simple expressions. And then using so we plotted the input impedance versus the normalized frequency, and here the plot looks something like this. And here one we obtained this bandwidth. So the maximum was achieved when Zin was at resonance, where Zin was equal to R, and at R by root two, we R by root two, we got this bandwidth over here, and this bandwidth is equal to the inverse of the quality factor. So this is important. This remains consistent throughout the series or parallel. In both of the cases, this particular formula is the same. Then we did a small discussion on loaded and unloaded Q. So we defined the quality factor for just the system over here as Q naught, and the total thing as Q or QL, and for the external circuit, the Q was QE. So these are the terms we defined, and we derive this expression over here that QL is equals to 1 by QL is equals to 1 by QE plus 1 by Q naught, and this holds for both series and parallel circuits. So and we also just I just put this table over here. So this is present in Pozar as well for quick reference. So it has all the important uh, terms that we derived in the class, and it is there also in the Pozar's textbook. Then we started with the transmission line resonators, where we discussed the short circuited lambda by 2 line, short circuited lambda by 4 line, and then open circuited lambda by 2 line. So for this, what we did was we took this transmission line section, and this particular transmission line section was we had L is equals to lambda by 2, and we wrote the expression for input impedance. And since the express this expression, this transmission line section is not lossless, we have alpha over here, and hence we are using this tan hyperbolic term over here. And the tan hyperbolic term can be expressed by using this expression over here. Now this tan, so we have the if the tan hyperbolic has an argument of a complex number, so this is how it will evaluate to. So we have tan h alpha L, tan beta L, tan beta L, and tan h alpha L over here. So now we need to evaluate these tan h alpha L and tan beta L. So that will do in the next slide. So we started with evaluating alpha L. We know that this alpha attenuation is very small, although it is not. We are not neglecting it, but it is very small, much smaller than one. And tan h alpha L for very small values will become equal to alpha L. Now we are now taking omega equals to omega naught plus delta omega, and delta omega is small. Then beta L can be written as omega naught L by Vp plus delta omega L by Vp. This particular term is actually equal to pi, uh, and this tan beta L is now tan pi plus delta omega by omega naught, and this thing will evaluate to this term over here. And for this, since this is also very small, we can equate it equal to delta omega by delta omega pi by omega naught. Now we have evaluated tan h alpha L and evaluated tan beta L. We just substitute them over here, and this is what we get. And now over here, this since this particular term is much smaller than one, we can just ignore this term over here, and this is the z naught expression. Now, if you compare this particular term is same as this term over here, the r equal to r, and this imaginary term is similar to this term over here. So we see that we see similarity in this Z input expression with Z input expression for series RLC resonant circuits. So we see that short circuited lambda by 2 line is similar to series RLC circuit. So we have derived the similarity over here. So hence, when we started with the discussion on the this for the resonators, we said that all like most of the microwave circuits can be either evaluated to series RLC or parallel RLC. So the hence we discussed these in detail earlier, and now we'll just show that this short circuited or open circuited transfer line sections can be expressed in either of these two ways. Now, once we have established that these look similar, we can just evaluate the resistance, inductance, and the capacitance by equating them. So once we had this resistance and inductance, capacitance can be calculated by using the omega equals to 1 by root LC formula. And similarly, once we have RLC, we can also evaluate the quality factor and similar. Okay, so this is we discussed in details, and now it's a similar thing can be done for short circuited lambda by 4 line, and in this case, once we evaluate the Z input and we simplify this tan H alpha quad beta L. So we are simplifying the Z input, and upon simplifying we get the Z input as this term over here. Now this term is similar to Z input for parallel RLC circuit. And once we see this similarity, we just equate them to get the resistance, capacitance, and in the inductance for the transmission line resonator circuit for short circuit lambda by 4 line. So very simple. To put in simple words, we are just finding out the input impedance for the short circuit lambda by 4 transmission line section, and we see we see that the Z input is either similar to parallel or series RLC circuit, and we then find the equivalent resistance and capacitance and inductance for the circuits. And once we have got this, we can also calculate the quality factor as well. Similarly, this can be also done for the open circuit lambda by 2 line. We calculate the Z input, and then the Z input comes out to looking something like this, and this particular input impedance is similar to the input impedance of a parallel RLC circuit. And then we can equate and calculate the resistance, capacitance, and inductance, and the quality factor. So I'll just take a pause over here. I quickly went through whatever we covered in the last class. If there are any doubts, we can discuss them now. Otherwise, we'll move forward with what we have to cover today from the next module. Okay, so if there are no doubts, we'll proceed. Um, maybe if so, I just saw pop up in my screen that there is some network issue. Uh, can you just confirm if I'm still like my screen is being shared and I'm still audible? So the network here is not that good.
Yes, sir, you are audible.
Yeah, okay, thank you. But when I hear your voice, it was breaking. So I guess the network is not that good. If just in case if you lose me, please do give me a prompt or just write in the chat or just interrupt me that my voice is breaking or you're not able to hear me. Okay, so we'll start with the next module. So the next module is power dividers and directional couplers. So we are slowly getting into different circuits, and so the previous module we looked at the resonators, and now we are looking at power dividers. So these are very useful components in microwave circuits and also directional couplers. So let's take a look at what these dividers and couplers uh, couplers are. Uh, these are circuits with, essentially in your well, if you are designing some microwave circuits, and you might have one particular source over here, and you might want to feed it to two different kinds of circuits, or you might want to divide this particular source into, or send the signal to two different places. And to do this, we need this power divider over here. And similarly, I think this should have been a coupler. Okay, so sorry for this typo. And a power coupler is when you have two signals, for example, signal one and signal two, and you want to send both of them to one particular block over here. You might need a power. You'll need a this power coupler over here. So sometimes in signal systems, like you must remember, right? You're just sending signal one and the signal two, and then this signal one plus signal two is happening. So this action is being done by a power this coupler over here. Or you might also want to, yes, for example, if you're sending one signal to one next point, and you might want to send the signal to a second place. So this coupler over here will just couple the signal from first path to the second path, and then send this to the next point. So essentially, like whatever these terms mean in like according to the dictionary, this they do exactly that. So if you look at if this is a power divider or coupler, so this will this is what if you want to divide this particular power P1 into P2 and P3 in this particular ratio alpha. So this particular this amount of power is sent to P2, and 1 minus alpha amount of power is sent to P3. Similarly, if P2 and P3 are there, then this power coupler will just add the power P2 and P3, and then give it at P1. So in power division, an input signal is divided into two or more output signals of lesser power, while a power combiner accepts two or more input signals and combines them at the output port. So one thing which I missed, so this power divider or coupler need not be just that we are sending one P1, and it can be only split into P2 and P3. It can be split into P4, as many terminals you want. So this can this so they also need not be of the same ratio. It need not be that P2 is equal to P3 equal to P4. It could be an arbitrary ratio, and it could be any number of power division. And similarly, any number of P2, P3, P4, Pn can be combined to get P1, and they need not be in the same of the same magnitude. So it may have three, four, or many ports, and we usually ideally want them to be lossless, but this might not always be true. But yeah, we ideally want them to be lossless. And power dividers usually provide in phase output signals with equal power division. Uh, uh, but unequal is also possible. So as I said, so they need not be equal, but usually we what we do is we make them with equal power division, and they usually give out the in phase output signals. For example, if so the phase thing is usually, since we are working in the microwave regime, the phase thing it's mostly dependent upon the path so if we are sending this signal over here, and we are receiving signal 2 and signal 3, if we're sending it at port 1, port 2, and port 3. And so if this particular path is longer than this particular path, then we will find phase difference. but we try to keep them in the same phase. Sometimes it might happen that you're trying to feed, for example, two antenna, A1 and A2, and you want them to be at some phase difference. So what sometimes we do is we make this power divider, and then we add some this particular extra path over here. For example, if we want to feed them at a 90-degree phase shift, so we just we bring in this 90-degree phase shift in this particular path over here. So this 90 degree, this antenna is A2 is working at 0 degree, and A1 is at 90-degree phase shift. So we're just changing the path length. We can manage this phase of the output signals. So I scribbled a lot on this slide. Any questions that you have from the like, the idea that you are trying to discuss about dividers and couplers? Okay, so we'll proceed then. For the power divider, the simplest type of power divider is a T junction. So any network which is gets spread like this, so all this will involve this particular section over here, right? So uh, this might look like Y or U, but all of them we call them as T junctions because they're splitting into two joints over here. Now the scattering matrix, if you remember, the S matrix for an arbitrary three-port network will have 9 dependent elements. So if they look, it will look something like this: S11, S12, S13, 21, 22, 23, 31, 32, 33. So it will have 9 elements, and if this particular device is passive and contains no anisotropic materials, that is, so this the anisotropy means if we have this particular material over here, so if the wave hits in this direction or it hits this direction, they uh, they will no anisotropy means this is isotropic and isotropic material. So this direction, the wave propagation will not depend upon the direction in which the wave is traveling inside the media. So hence we are suggesting this is isotropic, and this means that if this is reciprocal, so should it is reciprocal. Since it is passive and not passive and isotropic, this must be reciprocal. And for reciprocal system, this particular matrix will become symmetric, and hence this Sij will be equal to Sji. So we have suddenly give, these three terms will become equal to the bottom three terms, and so now we have lesser unknowns. So now only have six unknowns. To avoid power loss, we would like to have a junction that is lossless and matched at all ports. So this particular T junction will look something like this. And so over here we have one junction and three ports. And to avoid any power loss, we want all these ports to be matched and this particular junction to be lossless. But how it can be shown that it is impossible to construct such a three-port lossless reciprocal network that is matched at all ports. So we'll see that now. Why is it not possible? If all ports are matched, then we have S11, S1, S22, and S33. That is SII equals to 0. So for a if all ports are matched, then we have this S matrix over here. And now if the matrix is also lossless, then it will satisfy the energy conservation property that we saw. So this S matrix will become unitary. So we have seen this when we were discussing about S parameters, the scattering matrix becomes unitary if the network is lossless, and if that is true, then it satisfies all this six criteria. Now, equation D to F. So these three equations show that at least two of the three parameters S12, S13, and 23. Uh, so at least two of these three must be zero. So because the products of these their conjugates are equal to zero. So and this implies this at least two of them is equal to zero. And if that is true, if any two of them is zero, then this won't satisfy the top three conditions. This is in so however this condition will always be inconsistent with the one of the equations from A to C, implying that this three port network cannot be simultaneously lossless, reciprocal, and matched. So the, this was because it is matched at all ports, and this came in because it is lossless. And we have symmetry, and due to symmetry we have this these terms the same. So if we consider all of them, this particular criteria does not satisfy, since these, if two of them is zero, so this will so if we choose any two, for example, let's take 1 2 and 1 3. So if we take 1 2 and 1 3, so over here both of them are together, and if both of them are zero, this cannot be equal to 1. So if you take any of them, one of these equations won't satisfy. So this implies that it cannot be simultaneously lossless, reciprocal, and matched at all ports. So but if any one of these conditions is relaxed, that is, if it is either not lossless or reciprocal or matched, then a physically realizable device is possible. So it cannot be simultaneously. We cannot have all these properties, but we can have any two of them together. And if there is a three-port non-reciprocal network, and the conditions of the input, like we have all the ports as matched, and the energy conservation, that is it is lossless, that such a circuit is called a circulator. So we'll see this in the next slide. We'll design a circulator. So a circulator means that all the ports are matched and we have energy conservation, but it is not reciprocal, not reciprocal. RECIPROC, not reciprocal. So circulator is not reciprocal, and we usually depend on anisotropic materials like ferrite to get this non-reciprocal behavior in circulators. So before we start discussing a design of a circulator, any questions or doubts from what we discussed now? That why we cannot have a lossless, reciprocal, and matched network together in a three-port device? Okay, so we'll proceed then. So we have to demonstrate that any matched lossless three-port network must be non-reciprocal and thus a circulator. So let's start with the scattering matrix. So we have been told that it is matched and it is lossless. Okay, so if it is matched, then it implies that SII, that is S11 equal to S22 equal to S33 equal to 0. So we have the diagonal elements as 0. And now we have been told that this is a lossless network where S is unitary. This is unitary, so this will satisfy these six conditions because it has 9 elements. So we have these terms as this diagonal term 0, and so we have the simplified equations for unitary condition. And now since this is satisfied, and so this particular this six condition can be satisfied in either of these two ways. We can either have S12, 23, and 31 equal to 0, and mod of S21, 32, and 13 equal to 1, or we can have S21, 32, and 13 equals to 0, and 12, 32, and 31 with their mod equal to 1. So you can check this. If you can substitute and check, I'll leave this to you. So this can be satisfied in either of these two conditions, uh, so and this thing this if and this since this is satisfied in these two conditions only, this implies that this particular this implies that this Sij is not equal to Sji. So if you can see over here, so if we have S12 equal mod S12 equal to 1, we have S21 equal to 0. Okay, so so just from this example only we can see that this Sij is not equal to Ji, which implies that this particular matrix is not symmetric, and this implies not reciprocal. And this system is not reciprocal. The system is not reciprocal. To this particular network to be reciprocal, this S matrix had to be symmetric, which is not true over here. And since this can be satisfied in either of these two ways, so this is A criteria and this is B criteria. This For this A, we get this the S matrix looking something like this. Uh, so all these the diagonal elements are 0, showing that all the ports are matched, and this matrix is not symmetric, as you can see. For the second case also, we have this S matrix like this, and this is also not symmetric. If you look closely, for this particular S matrix, the circulator looks something like this, and what we have is the we have clockwise circulation. That is, if you send up some power at port 1, this will traverse in this direction, and so it can be at either what from port can be taken from port 2 or from port 3. So this traverses in this direction, and the opposite happens in the second case where we have this particular S matrix. So we have counterclockwise circulation in this second criteria. So any doubts from this? So we showed that we took the S matrix. We had matched ports. So we made the diagonal elements as 0, and then it was lossless. So we put the unitary matrix conditions, and then we showed that it can be satisfied in either of these two ways only. And for that case, we had Sij not equal to Sji, and which implied that the device must not be reciprocal, must be non-reciprocal. If no doubts, we'll continue then. Now the next question is we have to demonstrate that a lossless and reciprocal three-port network can be physically realized if only two of its ports are matched. So the previous slide we had the ports, all the ports were matched and the network was reciprocal. Now we have but we showed that it okay, sorry, we had all the ports matched and the network was lossless, but we showed that was non-reciprocal. But now we have the system as reciprocal and lossless, and we have to show that not all of its ports will be if only two of its ports match. So we assume that ports one and two are matched. So we have Z S11 and S22 as zero, and this, but we have been told that this system is reciprocal, and hence if this is reciprocal, this S matrix will be symmetric. So we have S12 equal to S21, S31 equal to S13, and similarly, so we have filled this matrix according to the conditions that we have been given. And now we have to if we put we have to now we see that we have been told that this particular network is lossless. So for lossless, we have this matrix as unitary, and we put in we try to observe the unitary matrix conditions. So if we expand these matrix for the unitary matrix, we get these six equations. And if you see from the equations D and E, this equation D and E over here, so we have S12, S12, S1323, and 1 and 1. So if you try to subtract them, we see that these two terms are equal. Just give me a second.
So your audio is not clear.
Yeah. So sorry about that. Am I audible now? Hi. Am I audible now?
Yes, you are audible.
Okay. Yeah. Thanks. Okay. So I hope you were able to follow me till here. So uh, we had ports one and two as matched. So S11 and S22 are zero. This network is reciprocal. So we have the this elements equal to these elements, and we have this network as lossless. So we have got this six conditions over here. And now according if it look at these six equations, if we look at DNEs now, we have S13 equal to S23 because the rest of the terms are equal. If we subtract them, we get S13 equal to S23. And this the, and using A now, so this we have S13 equal to S23. Both of them are equal, and if you multiply S13 with the conjugate of S13 with S23, and its product is equal to 0. But this S13 is equal to S23, and if the product of if they are the same, if they are equal, uh, so if their mods are equal, and if we multiply each other, both of them with their conjugate, and if that comes out to be 0, this implies that both of them are equal to 0. And this implies so if S13 and S23 are 0, uh, this implies that S12
So
and
your audio
S3,
is too low. I mean,
it's too low. Okay. How is it now? Is it better now? maybe I'll use a different device for audio.
Is it better now?
Yeah, better, but echo is coming.
Yeah, I could not hear you. Can you say something? Am I audible?
Yes, you are audible.
It's fine. Okay. Is it better now from the previous device?
I think from my end it is clear.
It's okay. Okay. Yeah, thanks. So I don't know how much you're able to follow. Okay, so I'll discuss this question again. So we had to demonstrate that we have that a lossless and reciprocal three-port network can be physically realized if only two of its ports are matched. Okay, so we have been told that the network is lossless, it is reciprocal, and two ports are matched. So we have written this. We have written the S matrix. The S matrix will have S11, S12, S13, S21, S22, S23, S31, 32, and S33. Okay. So we have this matrix and we have been told that two of its ports are matched and we're assuming they are 1 and 2. So S11 and S22 will become 0 and S12 will become equal to S21, S13 will become equal to 31 and S23 will become equal to S32 and the S33 will be there. And we have been also told that since this network is lossless, we will have this implies that this S matrix is unitary, and we know that for a unitary matrix, these things will be true. So, now we have got the 6 expressions over here. Now, and if you look at the equations D and D, they're same. They're identical except for S1. We have S13 over here, S23 over here. So if you subtract them, we get mod of S13 equal to mod of S23. And we also have equation A over here, which shows that S3 conjugate is equals to S23 equal to 0. So if their magnitudes are equal and the product of the conjugates are 0, this will imply that both of them are equal to 0. And if both of them are equal to 0, this means that these two terms vanish and we have S33 mod equal to 1 and S12 mod equal to 1. Okay, so based on this information, we can write a scattering matrix looking like this. So their mods are equal to 1. So we can since they and we have been to yeah. So we can write a matrix which looks like this. If you take the mod of these terms over here, they will come out to be 1, and yeah. And for symmetry, we are keeping these we can keep these two the arguments of these two terms as theta, and for the other element as phi. So if you and for this particular S matrix, we can also draw a signal flow graph. So it will look something like this. And if you look closely, this particular S21, S12, this particular network, if you put in some signal over here, that it reach and this so this whatever you send over here is same received from the other port as well, because they have the same we have this particular network has S21 equal to S12 for the reciprocity, and S33 is seems to since and this S33 is becomes isolated. So if you see that this network degenerates into two separate components, one matched two port line and the other totally mismatched one port line. So this particular thing is this particular port is mismatched. So this S33 is not 0, but for both of them S11 and S22 they are 0. So they are matched. This one is not matched, and they are reciprocal as well. So I hope you're able to follow this. Maybe my audio was not good for some time. And please let me know if you want me to repeat this problem. Also, I'll give you some time to go through this text over here so that if you have any doubts, you can ask. Okay, then we'll continue. So we'll start with this T junction power divider. So
Hello.
yeah,
Yeah.
hello.
Hello.
Yes, Anil.
Yeah. Can I ask one question here?
Yeah, sure.
Actually, this one input and two output ports you have taken. What if you
Yeah.
are having one input and three output ports are there? And generally, even number of ports generally we consider when we design these kind of power dividers. But odd number of power dividers when we want to have, then how do you describe this S parameters?
Okay. So yes, you can. Okay, you are saying this thing. For example, if you take this particular microstrip circuit, you are saying that what happens if we have one more port over here, right?
Yes.
Okay. So in that case, so the maths will become little different. So we'll see now when we are divide for this when we start with the power divider. So we'll look at the examples where we just have two ports, but so so this will become clear if we start with the resistive circuits where we'll have we have this, but just give me a second. So if we have three ports over here, then we need to for the microstrip line especially. So in that case, we need to divide the power into these three cases, and in that case, the if you're asking about the S matrix, this will again now since there are four ports, will this particular matrix will be 4 cross 4, and then again we'll have to if we want them to be matched, then we have to take care of the S112, S44, or if we have to keep, or we want all the ports to be matched, we have to make this diagonal element 0, and how much power in the what ratio we want to send in them, then we have to according to that we'll have to adjust the S12, S13, and S14 these terms. So depending upon how much power, for example, if you want them to be equal, then this S12, S13, S14, these terms will be equal. And if you want for example, this is 1, this is 2, this is 3, and this is 4. If you want this 2 and 4 to be isolated, then S24 should be equal to 0. If you want this 3 and 4 to be isolated, this S34 should be equal to 0. So this way you have to design the S matrix. And if you want to do it like visually how much power is needed, so once we have discussed the next two three slides, then it will become a little more intuitive on how we design the power dividers. So like I want you to were you able to follow this, and if you have any follow-up questions or you can repeat your question so that I can try to modify my
Yeah.
answer.
Yeah, this is okay. I'm following, but I want to know about that case when we try to design microstrip line. Say generally
Okay.
when we divided equal power ratio, one is to 1 to 2 power divider. When we try to
Hmm.
divide it equal power ratio. Then we take
Yeah.
root 2 times of that output impedance Z naught. But
Yes.
when we try to have three output ports, odd number,
Okay.
then it will be, can it be root 3 times or any other method?
Yeah, okay. So let's look at the next slide.
Okay.
So,
Yeah.
okay.
This is my question. Just keep it aside,
Yeah,
and
okay.
then you can.
Yeah, sure. So we'll discuss now the two ways when where we have the lossless power divider, and then the other is the resistive one. Once we have done that, maybe if you still have the question, we can discuss on that. Okay.
Yeah.
So these are the famous microwave circuits that we often see in the lab. So this is an E plane T, this is an H plane T, and this is a very common microstrip line where we have this power divider. So we there's also what I saw in our lab. There was something which was called a magic T, which had these two things as combined. So this particular terminal was also present over here like this. So this thing could also come like this. So just for information, this can be combined, and this you will have your H plane T in this plane over here, and in this plane you will have your E plane T, and we call this as magic T. And this is just a plain PCB, and where you have this microstrip line over here, maybe ground pin at the bottom, and this is the power divider. So we'll look at the mathematics, some mathematics in the next slide. So let's look at a simple lossless divider. So what we have over here is we have this microstrip line over here with Z0 impedance, and the characteristics impedance is Z0. And we want to divide the power in this transmission line into these two arms over here. So one thing happens is we might have fringing fields at this particular junction over here, and this junction may or may not be lossless. So if we have some losses over here, this is usually accounted by bringing in this lumped susceptance JB over here. And if we want this particular this junction to be matched, what we have is since these are in parallel, we are taking in admittance over here, and this admittance in is equals to JB plus 1 by Z1, this term over here, plus 1 by Z2, admittance from here, and which is it is equal to the characteristics impedance offered by this first line over here by Z0. So from your previous question, as you said, Anil, I believe, yeah. Uh, as Anil asked in the previous slide, what happens if we have three arms over here? So if we have one more arm over here, like this, we have Z3, then we will, this particular equation will be modified to have JB plus 1 by Z1 plus 1 by Z2 plus 1 by Z3 equals to 1 by Z0. Okay. So if there are three arms, we will have one more term over here. If we have more arms, we'll add more terms over here. But if we assume this junction to be lossless, or the losses are very low, then we can ignore this this B term over here, this termed element term over here, and this is the equation that we will work with. And if there are one more arm over here, this will become Z3, and similarly if there are more arms. But in practice, this may not be negligible, and we might have to use some reactive tuning to get uh, to balance this. But we will not concern ourselves with this right now. We're just looking into maths, and this is something, if you go with fabrication, and that time you can deal with this. So there are methods to do this. You can look up on some papers on IEEE, maybe textbooks. Okay, so let me just, okay, so we'll just finish this and then go back to Anil if he has any questions on this. So so let's take an example. If this particular power divider was supposed to have, we were supposed to this particular input impedance was 50 ohms. We had this impedance as 50 ohms, and we wanted to divide the power equally in both these arms. So in that case, this Z1 and Z2, both of them will become equal to 100 ohms. Because if you want to divide the power equally, we will have this Z1 equal to Z2, and we will have 2Z1 equal to 1 by Z0, and sorry, 2 by Z1 equal to 1 by Z0, and we substitute the value of Z0 as 50. We will have Z1 equal to 100 equal to Z2. And if necessary, a quarter wave transformer can be used to bring in the output line impedances back to the desired level. So what is said over here is that we have this 50 ohm impedance over here, and then we have divided the power into 100 ohm impedances over here. But we have a load, for example, ZL, which is 50 ohms, right? So we want to match it to this Z1, and so we saw in the previous modules that to match this, what we can do is we can use a quarter wave transformer over here, which will match it to the 50 ohm. So we can use a quarter wave transformer. So this is 50 ohms and this is 100 ohms. We can calculate the Z quarter wave transformer equals to root under 100 into 50. We'll get this as something 70. Maybe you can do this math to match this 50 ohm load to this 100 ohm impedance of this power divider line. So if the output lines are matched, for example, so if we have included this quarter wave transformer and matched it to this 50 ohm line, so if this is matched, then and similarly, if this arm is also matched, then this entire structure will be matched. And there will be no. But one thing that we have to notice is that there is no isolation between the two output ports. So if we say, so just in case, if we are sending okay, so we are sending power from here and we are receiving equal power over here. But if what happens is if some power is sent from here, this particular thing will become this junction will not be matched, and in that case we will some power will be reflected from here, power will be reflected from here, power will be reflected from here. But if you're sending power from here, and if this port is matched over here and this port is matched over here, and this junction is lossless, and in that case, no power will be reflected back. So, so Anil, was I able to like answer some part of your question? Any follow-up questions on that, and any follow-up questions on what we just covered now?
No. So as of now, what I understood that I have to add one more here, 1 by Z1, Z1 plus 1 by Z2 plus 1 by Z3 should be equals to 1 by Z0. For
Yes.
equal ratio case, then I have to take that. Accordingly, I should take one impedance here, and then accordingly, I have to use one quarter wave transformer to match the output load.
Yes, correct. Yes, correct. So, and that's all. And so if you're already working with microstrip lines, so you must know that if you know this impedance value, then you can calculate the thickness of the microstrip line. So and for fabrication and all the works, you only need to know how much thick the line has to be, and that depends upon the impedance. And once you have already substituted this Z3, for example, over here, or as many impedances that you want, you can calculate these impedance values depending upon how much power has to be spent on each arm, and then you can find their values and then find out the thickness of this microstrip line, and then you'll be done with your power divider.
And one more question that see, the thickness determines the impedance. Does the length will affect on the phase that offered by that microstrip line?
Yes, the length will affect the phase. So if you want all the arms to give, if you want all
same
the
phase
arms
should be given.
Same phase, then you have to make sure that each of this length is equal. And if you want to, for example, if you're feeding some antenna array and all this, so there should be some progressive phase difference, phi 1, phi 2, phi 3. They have to some progressive difference, and you'll have to make sure that this phase, this progress is dependent, consistent with the extra length that you are adding or the length you are changing. And if you want them to be of this fed at the same phase, you have to make sure all the arm lengths are equal.
Okay, one more question, that the length determines the phase, but when we try to make that particular length from the input port to the output port, we'll have multiple impedances, right? Input side 50 ohm, at the end 50 ohm. In between, we have some different kind of impedances. So that particular impedance length also will affect, or it will consider it as overall length. For different impedance, for different length, we will be trying to use in order to match the output impedance.
Anil,
Should I
just give me a just give me a second. So I have just give me a second. I'll come back to you and also a question. Just give me one second.
Yeah, sure.
Yeah. Sorry. Can you please repeat your question, Anil?
My question is that in order to have a particular, all ports should have same phase. Okay. So the
Yes.
main thing is that we need to maintain the uniform length. That input to
Yes.
output port, we have to have uniform length. So in
Yes.
order to maintain that input and output length equal, input side we have 50 ohm and output side we have 50 ohm. In
Yeah.
between, in order to divide the power, we'll be using different impedance impedance strip lines that we use.
Yes.
Okay. Does that also affect the output power division, or else that length that we use actually for different, for example, if we take 100 ohm case, we take div of length of 10 mm if we consider, and next in order to match that with 50 ohm, we use some intermediate impedance of 10 mm or 15 mm we take, and output side we have again 15 mm. So does this overall length it will consider, or else for a particular impedance for particular length it will take like that?
No. So the phase will be independent of the how much the thickness of the line is. So the phase will only depend upon the total length of the line,
Okay.
irrespective of the impedance. So I get your question. I think you're asking is, for example, we have this 50 ohm over here, and then we divided this into 3 arms. Okay,
Yes.
and
Yes.
this was 50, and this became 100 ohm. Yeah, right. This
Yes.
this all this is 100 ohm, and then we wanted to get 50 over here. So these are 50 ohm lines, and then in between we use some quarter wave transformer.
Yes.
Yes, right. We use some quarter wave transformers, and we want all of them to be of the same phase.
Yes.
Right. So
Yes.
what happens? So how should we take in the line? So this entire line, for example, if I'm drawing this particular length over here, this is as L1. This entire length is L2, and this entire length is L3. So this L1 should be equal to L2, should be equal to L3, irrespective of the impedances of the thickness of the line.
Oh, okay. So that input length will not be considered. Where we are taking the division, power division is happening, from there only it will consider for phase.
Yeah, even if you consider this thing line, so you want so the phase depends upon the total length traveled. Okay, so for example, if we had some phase for phi 1 over here, and we are receiving some phi 2 over here, and we want phi 2 and phi 2 over here as well. So this total length, okay, from this P1 port to P2 port or P3 port and P4 port. So the total length between the total length traveled by the wave from port P1 to P2 should be equal to the total length traveled by the wave from P1 to P3 and P1 to P4. So this total length should be same for all the ports. If that is true, then we will receive same phase difference between these two ports.
Okay, thank you.
Any other question? And Anyone else? Else will proceed to the next topic that we have. Okay, so we have one more example. For over here, what we want is we have to determine the output characteristic impedances. This is Z1 and Z2 over here, and we have this input impedance of Z0 as 50 ohms. Sorry, I missed this ohm over here. A lossless T-junction power divider has a source impedance 50 ohms, so this is 50 ohm. We have to find Z1 and Z2, the output characteristic impedance, so that the output powers are in the ratio 2:1. So we have this particular, we have to divide the power in 2:1 ratio. So one arm will receive twice the this is 1x, this will receive 2x. And if this total thing is 3x. So, and we also have to compute the reflection coefficients looking at the output port. So reflection coefficient, if we are looking from this side. So if this question is clear, then we can start by solving. Okay, so the first step is we assign this particular voltage V naught over here. So this particular voltage as the junction is V naught, and the input power can be now given as PIN as half V naught square by Z naught. So this is very standard. So we've calculated the input power over here. So we have P in power over here, and according to this, if the power over here should be 2 PIN by 3, and the power should be PIN by 3. So this port receives twice the power of this port. And the output power over here can be given as half V naught square by Z1 and half V naught square by Z2. Okay, so let me just change this back to this over here. So this particular port is receiving 1x power, and this particular port is receiving 2x power. So we have power as PIN by 3 over here, and also the output power is given by half V naught square by Z1, and this half V naught square by Z naught is PIN. And so using this these two expressions, we can find out the value of Z1, and using these two we can find out the value of Z2. Which just substitute this PIN over here, which is half V naught square by Z naught, and we can calculate this, cancel this, all these things. We have 2 by 3 over here. So this Z, the Z2 term comes out to be 3 Z naught by 2, I believe. Yeah. So and similarly, if we substitute this P1 over here, we have Z1. Any questions, Anil? I'm still audible, right?
होगा तो सर मैं मेल पे मंगा लूंगा आपको। हाँ, इससे ज्यादा क्या है, मेल से ले लेना।
I believe your mic is on. Maybe Anil, your mic was on, so I just muted you. If you have any questions, you can unmute yourself and ask. So there was some noise. Okay, so substituting this P1 PIN into over here, we can get we get the value of Z1 as 3 Z0, and similarly, if we substitute this PIN over here, we get Z2 as 3 Z0 by 2, and substituting the value of Z0 over here again, we get Z1 is equals to 150 ohms and Z2 equal to 75 ohms. Okay, so now we have got Z1 and Z2, which was asked for us. We had to calculate, we had to find out the output characteristic impedances. And now the next step is to find out the reflection coefficient at these two arms. And just to verify, we also calculated these input impedances, and if you since they are in parallel, if you calculate their value, this turns out to be 50 ohms. So this Yn is equals to 1 by Zn is equals to 1 by 50. So which is okay. Then hence the this junction is matched. And now if you look at from this point over here, okay, if we look at this this arm over here, first we see is this this is Z1, right? So this first we see is 150 ohms, and then at over here we see 50 ohms, and this particular arm has 75 ohms. So if you coming from this direction, first you see 150 ohms, and then you see 50 ohm and 75 ohm in parallel. So for that and if you take calculate the parallel impedance of this 50 ohm and 75 ohm, this turns out to be 30 ohms, and this 30 ohms is in now series with 150 ohms. Okay, and similarly, if you look from this direction over here, if you look from this direction over here, this is 75 ohms, and then 75 ohm sees 150 ohm and 50 ohm in series. Okay, so 50 ohm and 150 ohm in series is 37.5 ohms, and the deflection coefficient can be now calculated using this thing over here. This is 150 ohm is the transmission line impedance, and the load impedance is 50 parallel with 75, which is 30 ohms. So, ZL minus Z0 by ZL plus Z0, 30 minus 150 divided by 30 plus 150, and this entire thing comes out to be minus 0.66. And similarly for the reflection coefficient seen from here, gamma 2, and this was gamma 1. This is 75 ohms, and which is in and the load impedance is 150 and 50 ohm in parallel, which is 37.5 ohms. So 37.5 minus 75 by 37.5 plus 75, and this comes out to be minus 0.33 ohms, minus 0.33. So I've calculated the reflection coefficients as well. So we calculated the input impedances that we were supposed to do and the reflection coefficients. So any questions on this example? Am I still audible? I did not get an answer previous time. I hope this all was this you could hear.
Yes, sir.
Yeah, thank you. Okay, so I hope this was clear, because this particular problem was pretty straightforward. So I hope this won't be you won't have any problem with this. Any following any question similar to this? Okay, so we'll move to the next topic, which is the resistive divider. So up in the previous case, we were assuming the this power divider to be lossless. Okay, so if the 3-port divider contains lossy components, it can be matched to all the ports. So the issue with the previous case, if you as you saw in the example, was that if you we only had S11 equal to 0, but S22 and S33 they were not 0. So if you saw from this port over here, the reflection coefficient was not the reflection coefficient was not 0, and similarly from this port as over here as well. So we had some reflections coming back from this junction over here and these two arms over here. If we sent some if we send some power from here, similarly if we send some power from here as well. So but if we but in the case of a resistive divider, we can match all the ports. So if we send any if this particular port or this particular port or this particular port was like from all these ports, we will not receive any reflections. So over here we have this particular power divider, just a power divider over given in this figure, where an equal split 3D, which is minus 3 dB divider is shown, but unequal power. Yeah. So, okay. Sorry. So this particular thing shows an equal power divider, but we can also do this for unequal power divider as well, and we can and then using a resistive power divider we can match all the ports. So for this particular resistive power divider, what we see over here is this particular Z, if we calculate, uh, we have this Z naught by 3 resistor over here and Z naught resistance over Z naught the characteristic impedance of this transmission line. So they are in series, and hence this particular Z uh, and hence this particular Z turns out to be 4 Z naught by 3. And if you calculate the input impedance over here, then we have this Z naught by 3 over here, and then we have this Z Z from here and Z from here, and both of them are in parallel. So this since they both of them are parallel, this becomes half. Uh, this becomes Z by 2 at this particular plane over here. So this is Z 4 Z naught by 3, and this becomes half since both of them are in parallel, and this total Z input impedance becomes Z naught. This particular this so what we're seeing over here, this Z naught. So this Zn is equal to Z naught, which is equal to the matched, which is equal to the characteristic impedance of this transmission line over here. So this is matched, and since this is symmetric, if you see from all the ports, uh, if you see if you started calculation from here as well, so this will appear same. So all the ports are matched from are matched. If you try to calculate the Z in over here or calculate the Z in over here, they all will turn out to be Z naught, which is equal to the characteristic impedance of the transmission line next to them. So this can be seen from the symmetry, and we just calculated it from Z in over here. So all the ports are matched, and this implies that all the S parameters, the S11, S22, and S33 are all since they are matched, they are equal to 0. So this was not true for the previous lossless case. So before I continue, any questions on this? So earlier, when we started the discussion on power dividers, we saw that we cannot have a lossless, non-reciprocal, and a power divider which is matched all the ports at the same time. So every time we will if we satisfy two conditions, the third will not be able to satisfy. So the previous case it was lossless, uh, but we could not match it to all the ports. But over here we are matching it to all the ports, but we have included this lumped resistors over here, which will dissipate power. Okay. So if you're calculating the voltage at port 1 V1, then by voltage division, we can calculate Am I still audible? Something happened to my system. Is the screen still visible? Vinay, can you confirm? Yes. Screen is still visible, right? Okay, I cannot see my screen now. Okay, maybe it will come. Okay, so we are trying to calculate the voltage at port 1, and this using the voltage division. Okay, something is not right. Uh, okay, yes. This my laptop keeps turning off. Just give me a second. I'll just plug this in with to the charging port, and then see if that works. Just give me a second. Uh, I hope this works now. Okay, so once we have calculated, so we're using this voltage division at at the junction, and we are calculating the voltage V over here. Once we have this, we're sending V1 over here, and we're calculating V over here, and this turns out to be 2 by 3 V1. So this is straightforward, pretty straightforward. This we have Z equals to 4 Z naught by 3 over here. So and the total thing over here is 4 Z naught by 3. So this if you look at closely like this, we have V1 over here, we have a resistance some Z naught by 3, and then we have 2 Z naught by 3, and then something round over here. So the voltage over here will be using the voltage divider. We get this as 2 by 3 V1 across this, right? So so we get V as 2 we get this V as 2 by 3 V1. And similarly, we have V2 and V3. By again using voltage division, we are calculating V2. They have voltage V over here. So this is some we have voltage V, and then we have Z naught by 3, and then we have Z naught over here, and we're trying to calculate voltage over here, and this turns out to be 3 by 4 V 3 by 4 V, and this is 3 by 4 V, and this is since we know that V is equals to 2 by 3, this is half V1. So this V2 is equal to half V1, and similarly this V3 is also equal to half V1. So we are sending V1 over here, we are getting half V1 and half V1 over here. So we are dividing this voltage equally, and we have it's equal impedances all around. So we are distributing the power equally. Hence in this case, the S21, S1, S31, S23, all of them are half, because the voltage which we are sending over here, so the voltage becomes half, and the power becomes 6 dB over here. So we are sending 0 dB over here. We are receiving uh, minus 6 dB over here and minus 6 dB over here, something like this. And this particular network is reciprocal. If you see by just visually, we have symmetry over here, and so this particular network is reciprocal, which implies the scattering matrix is symmetric, and it can be written as this matrix over here. And the power delivered to the input of the divider is, so we have V1 over here, right? So we can write this, the power PIN as half V1 square by Z naught, and the output powers are actually half V1. So which is, if you substitute this over here, this we get this as 1 by 4 PIN. So this if you calculate this, this is if your PIN is 0 dB, this total thing will minus 6 dB. So the half of the power is dissipated across these resistors. Okay, so before we start with the Wilkinson power divider, I'll just pause over here and let you go through this. If you have any questions, you can ask me maybe now. So I'll let you read this. So using a resistive power divider, we have designed a network which is matched at all the ports, and which is also reciprocal, but it is not lossless. Not lossless. Okay, so the next topic is the Wilkinson power divider. So the previous resistive power divider also, there was one issue that if you say the system was reciprocal, and also these ports. So we had P1, P2, and P3. So if we send so the first and second ports, the lossless one and the resistive one, in both cases, what happened was, if we sent P1, we got equal power in P2 and P3. But if we sent if there was some reflected, something got reflected back, or like if we sent some power from here, it saw either mismatch, or they were not isolated. So if something got reflected back from P3, it will also affect power in P2. If something was reflected back from P2, it will also affect the power in P3. So one thing that was missing was that these ports were not isolated, and we want these ports to be isolated. Please let me know if there is a significant lag, because I just changed my place from one place to another, and I believe the signal strength is not good here. Okay, so lossless T-junction divider suffers from the disadvantage of not being matched at all the ports, and it does not have isolation between the output ports. So these ports are not isolated, and it also does the it is not matched if it is lossless, and if it is lossless, it is not matched. So we want something in between in these cases, and the resistive divider had matched, but even though it is not lossless, isolation is still not achieved. in the resistor divider, we achieved one thing that it was matched at all ports, but although we it was not lossless, but we did not achieve isolation between the ports. However, from the previous discussion, we know that we can design a lossy three-port network which can have all the ports matched with isolation between the output ports. So this is what we have been looking forward to. We want isolation between the output ports. And Wilkinson power divider is one such design where we can even have arbitrary power division. So it need not be that what power we are sending, it should be 1:1 ratio. It could be in 1:x ratio, or we'll also see that it can be into 1:x is to y is to z, any number of ports, output ports, and any number of arbitrary power division can be done using the Wilkinson power divider. So, but the analysis for this arbitrary thing is out of scope for this particular course. But there are papers out there which you can refer to if you want to work on these. So this Wilkinson power divider is often made in microstrip line or strip line. It is shown over here. Like this is what it will look like. So it is like every other power divider. We have this T junction over here, and then this power is divided. For example, if this was 50 ohm, this could be 100 ohm. This could be 100 ohm, and then we have this quarter wave transformer to match this to this Z0 over here. One thing that you notice is that we have added one resistor over here, and this helps us to isolate these two ports. If this is port 1, this is port 2, and this is port 3. This resistor over here is isolating basically this port 2 and port 3. To analyze this particular Wilkinson power divider, we'll be using this very old technique called odd even analysis. So we'll divide this circuit into two cases. When we give according to the voltage input that is given to the circuit. So for the even odd mode analysis, we are modifying this particular circuit to the circuit over here. So this transmission lines are over here, and they split this port at this this particular junction is now being split. So this V1 plus V1 voltage is given over here, and we have port 1 over here, port 2 over here, and port 3 over here. Okay. So this and we have normalized this particular circuit over here. So this particular Z0 is equal to 1. This okay, this Z0 divided by Z0 is 1. The Z0 divided Z0 is 1, and this particular Z0 is now, since now it is split into 2 and they both are in parallel. So this Z0 by Z0 was equal to 1, but after splitting, this both of them have become 2. So that once you keep them in parallel, they become equal to 1. We have added some voltage VG2, VG3 over here for analysis. And this particular resistance was 2Z0. We have after normalizing this became 2. So to get this value, we will be solved. So before, so right now we are assuming the resistance to be R. We'll evaluate to find out this R value, and since this is in series. Since this is in series, we have split this into R by 2 and R by 2 over here. So if you look closely, we can draw a mid plane from here to split the circuit into two halves for further analysis. So I'll just pause over here so that you can take a look at this circuit over here before we split this circuit into odd and even modes. If you have any questions, you can ask as well if, regarding this, how we got this these values over here, or how we got this equivalent circuit. Okay. So once we have got this particular circuit over here for odd and even mode, what all we need to do is we put VG2 and VG3 both as in both cases we give 2 V naught in the two sources. And in case of this is for even mode, and for odd mode we give 2 V naught over here and minus 2 V naught over here. And in both these cases, at these junctions, at this junction, the circuit assumes different values, and according to that we split the circuit. So if you take a look, if this is 2 V naught over here, in that case what will happen is this particular if both of them are 2 V naught, this particular port will become open circuit over here. We'll see that how that happens in the coming slide. So if this particular point become open circuit and this also point becomes open circuit, in that case what we can do is we can simply open the circuit from the middle. And this happens for the even mode. And for the odd mode, what will happen is this becomes short circuit and this also becomes short circuit. And in that case, we can again isolate the above part with the below part. Okay. So I hope this is clear. And how this open circuit and short circuit thing happens is what we will cover in the next few slides. Okay. So we have for even mode analysis, we have this VG2 as 2 V naught and VG3 as 2 V naught, and this both of them are at the same voltage, since there's the same potential over here, and this circuit is very same as this since it is symmetric from this point. So we will the potential over here, whatever this potential may be, this plus V2 and this plus V3 over here, this they both of them will be at the same potential, and hence no current flows from this path. Since no current flows from uh, this path, there will be a okay, sorry, this is at the same I hope I'm still audible. So we have some potential over here, V2 and V3, and then again this port over here as well. And this particular port, I hope I have. Just give me a second. Okay, I believe I'm still having this network trouble. So what I can do is maybe this I can stop over here and can continue with the Wilkinson power divider in the next class. And yeah, because I'm still not sure how to figure out this network thing at my home. I'm actually visiting my hometown. So let's do that. I'll figure this out. This maybe use my personal hotspot the next class. Uh, I've been running between different rooms. Okay, so let's end it today. I'll start the Wilkinson power divider again in the next class. And we only have a couple of slides for the Wilkinson power divider. Yeah. Okay, maybe I'll exit this over here. Yeah, we only had a like couple of slides more, 3-4 slides. So we have covered so we have covered 3-port networks and T-junction power dividers. This we will do it in the next class, and then start with 4-port networks as well in the next class. And yeah, so I'll share the slides with the Wilkinson power divider today itself, and uh, so you can go through that as well. Okay, so I'm so sorry for the all this network trouble. See you in the next class. Yeah, thanks for joining.